Okay, so we're going to look at graphs of the radiation that we've been talking about. Oh, my projector. Maybe you can move a little right. No, the other way. No, the other way, the other way. This way, yes. Yes, yes, yes. Okay. Yeah, it'll be fine. Okay. Graphs. Yep. So we're going to look at graphs of log A and log N, basically. Okay, so let's have a start. So below, I'll have some data for a radioactive sample, and you can see the A decreases. But of course you knew this already. So I'm going to use an office program to draw this graph, but in the exam you will need to use graph paper, of course. So anyway, what you need to write down is this data here. So just write this data down. I think this, I should have said here the N. Well, anyways, you're not writing this down.
Oh, so it's N, not A.
Yeah, it's M, not A. So I'll need to fix that. Anyways, I just need this table. You have this? Yeah? Okay. So, sorry, just a sec here, so I don't forget. Now, I'm going to use Office, but in the exam, you need to use graph paper. DN. Okay. Now I need you to give me the data. So in the first one here we have time, and that's in seconds. And the next one we have N, and I'm using moles here because it's so large. So I know the time goes all the way up to 10. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and the first one here is 10, isn't it? Oh, 100. Yeah, I know that it halves every 2 seconds, doesn't it? Hang on, I'm going to cheat. It's like this, isn't it? Well, I have more numbers here than what you have, but that's okay. What is it, 3 decimal places, or? Doesn't matter. I have more, that's fine. Okay, so let me draw this. Okay, so I want a nice graph, like it with the lines. And my title is, I don't know, just an example graph. And the x-axis, what goes in the x-axis? The time, and the unit is seconds. And on the y-axis is the number of atoms, the n, the number of atoms, and I'm using moles here. Okay. And this is what the graph looks like. Let me just make it a little bit smaller. So you see it has this nice decreasing shape to it. Now I'd like you to copy this in your notebook. In the exam you will need to do this neatly on graph paper. There, where did I put my key? Uh-oh.
Which key? Open the door key?
Yeah, open the door key. Oh dear. I'm in big trouble if that is it.
Where's your key?
Huh? Did she take it?
Sure.
Maybe she did.
Yeah, I think.
Maybe she did take it. You saw her take it?
I don't know, maybe you put in the table, maybe she, it says she released.
Yes.
Yeah, I think.
Oh dear, oh dear, oh dear, oh dear, oh dear, oh dear. Uh-oh. Oh wait. Maybe.
Yeah.
Maybe.
Oh!
Alright, did you draw that now? You drew that? Nah. Okay, but at least write the names in. Okay, you got that one? Great. So, as you can see, the graph is exponentially decreasing. And of course this is not a surprise. But what's difficult, you don't need to write all of this down, Louise, it's okay. What's difficult is that you can't get much information from the graph. Like, for example, I can see what the n0 is. So the n0 is the n at the start, and what's that here? You see it's 100. That's the n at the start. But you couldn't, for example, see what the decay constant is. You know, this graph is good, but it's not so useful. So we need to do something about this. So what I'm going to do now is calculate the log of the n. So for example, here is 100, and underneath it is log 100. And here is 70.7, and underneath this is 4.26. Yeah, so add to your table this extra row. notice that the units for log n are log mole. Yeah? You have all those numbers? Yeah. So let me go back now to my Office program here, and let me get rid of this graph. So difficult to delete graphs, I don't know why. Yeah. So what I need now is another column called log of n, and the units are log mole. So this here is ln of that one. 4.61 was the first one? Yeah. Okay, so now let me graph this. See what I get. So I have my scatter with my points. Okay, and I'll call this one example again, and it's time in seconds, and the y-axis this time is log the number of atoms, and the unit here I will be using log moles. Now, look at what's happened to the graph. Yeah, it's a straight line now, isn't it? This is much more convenient for us to draw and to use. So we should usually put the log on the y-axis. This should be easier to draw. Got that? Yeah? Yeah? Okay. Louise? Yeah? Okay. Now, notice now how my graph is linear. Okay, so what's happening here? Let's have a look at what's happening. So we have this formula for n, n0 e minus lambda t. We all know this. Now what I'm going to do is I'm going to put a log on both sides. So on the left, I get log n, and on the right, I'll get log n0 plus log e minus lambda t. Now, if you remember, I'm using the first rule of logs. log AB is log A plus log B. You remember that rule? And now I have log n equals log n0 minus lambda t log E. Because next I can bring this down. That's like rule 4 or something. What's log of E? It's 1. So you get log n equals minus lambda t plus log n0. Or if you want, log n equals minus lambda t plus log n0. Now I want you to compare that to, we put log n on the y-axis, yes? So this is like y equals, now what do we put on the x-axis? What do we put? The t. Yeah? So can you see now that the equation we get is like a straight line? Y equals mx plus c. When we use log n on the y-axis and time on the x-axis. So this is why we get a straight line. And in fact, what can we say the slope of this line is? Minus lambda, yeah. And the c is log n0. So if I go back here now, if I put log on both sides, what happens? I get this, log n equals minus lambda t plus log n0, which is what you wrote down. And so, the y is log n, it goes on the y-axis. The x is the t, it goes on the x-axis. The n, which is the slope, is equal to minus lambda. And the c, which is the intercept, is like log n0. Now, if you can just make, like here, if you want, you can just say, you know, the n is the minus lambda and the c is the log n0. Yeah? And the story is the same for A. You don't, N or A, it doesn't matter. Okay. Now, I have a question here, but maybe just before I do that one, let's go back to my graph, for example. Whoops. So I want to calculate the slope here. Let me actually shrink that a bit. Okay, so you know you have to make your triangle for the slope. So the m equals okay, and how high, or what's the height of this triangle? It looks like it goes up to 4.5? 4.61, and down to, what is it? 1.14, yeah? And then, oops, the base of the triangle would be 10 to 0, so it's 10 units long. And actually, really, because it's going down, it's a minus. So this is the m, minus 0.347. So what's the lambda? Well, that's 0.347. Now, I can also calculate the half-life. Do you remember the formula for half-life with the lambda in it? I think it was like this. Lambda t a half equals log 2. We did this last time? Yeah, you can check your notes.
Yes.
So the half-life is log 2 divided by lambda. So if I go back now to my graph, sorry, you need this, Louise? Yeah. So if I go back to my graph, if I do here the half-life, that's equal to log 2 divided by my lambda. So what's the half-life here? 1.99, or in other words, it's roughly equal to 2 seconds. Whoops, not square root. It is roughly equal to 2 seconds. You see that? Yeah. Now, does that make sense that it's 2 seconds? Well, it does, because if you go back to the data, at 100, how long until there's half? 2 seconds. How long until there's half again? Yeah, 2 seconds again, up to 4. You see? So it should not be a surprise that this was 2 from the calculation. Yep. Also, here, what's the c, the intercept? 4.61. What is it? 4.61. Now, what does the c represent? I think that's log n0. So log n0 equals 4.61. So that means n0, how do I cancel a log? What cancels log? E, yeah. So I think it's exp for e, I think. I hope. Sorry, I think you have the wrong room. Oh, come on. 100.48, or roughly equal to 100. But what is the n0 for my data? It is 100. So, I'm trying to make it clear to you that these graphs, the log graphs, are very useful for these problems. Okay. Now, let's have a look at an example. So let me go back to the data here. Okay, now in this one it's activity. It's activity here. So I need you to write this data down, please. Got the data? Okay, so, actually that's kind of a silly question because I can see A0 is 10. Anyways, what would you need to do first for you to make the graph here? What's your first step? log A. So what I want you to do now on your calculator is write in here the log A of all of these, okay? So you need an extra row now. This is what it's like when it's in the exam as well. You have to first do the log calculation.
So log A is the log 100 and then minus.
Yep, ln 100, yeah. Got it? Same time as me. So you should have numbers that look like this. 2.3 down to 0.57. Roughly, yeah? Okay. So now, next step. I realize now my first question is kind of silly. Let's get rid of that. Okay. Back to the question. So forget about that part. The first part is from your graph, estimate the lambda. So I suppose, actually maybe my first question should be, graph this in an appropriate, Okay, so the first thing is just draw the graph. So you can draw the graph too, and I'll draw the graph together. So you put the time on the x-axis and your log values on the y-axis. So let's do that. Got your graph? Okay. So I'm going to calculate the slope. So what's the biggest value here? 2.3. And the smallest value? 0.57. And then the base is 10 long, isn't it? So divide by 10. So I got my slope as minus 0.173. So that means my lambda is equal to 0.713 seconds. sorry, 1/2. So that's the K constant first, the lambda. Okay, so by the way, actually, what's the C here? It is 2.3. Okay. Right, now we have a lambda. So next, tell me what is the half-life here. So what's the half-life? Yeah, it would be, let's see, half-life equals ln2 over that number. So what do you get? 4 seconds, basically. Do you get 4, Louise? For this? No? You are using this formula. Yeah? So, type in on your calculator log 2 divided by 0.173. Yeah, 4 seconds, yeah, okay. Now, what is the n0? Now that's interesting, what is the n0? So, we have this formula, if you remember, A equals minus lambda n. Isn't that it? That's it. Yeah, I gave it to you 2 classes ago, wasn't it? So A0 is equal to minus lambda n0. So if I want n0, that equals A0 over minus lambda. But anyways, the minus and the minuses here cancel. So really it's just the A0. What's A0 here? I think it was 10, was it? And the lambda is 0.173. So what do we get here? 57.8 atoms only. Now these aren't moles, because I didn't say I was using moles, so it's just actually 57.8 atoms. Yeah. Yeah? Okay. Sorry, back to my question. Right. Now, the last part is what is the n when t is 11? So what would be the next number here for n? Okay. So what formula do we use to calculate n? What do you think? Yeah? No, you were doing fine. N0? Yeah. Yeah. Now the question is this. Do we know N0? We do. What was it? 50 something. And do we know the lambda? We do. And do we know the t? Oh, we do. So give me the n, please, at 11 seconds. If I look at my table here, I feel like the answer should be something like, oh, I don't know, 1.5 or something like this. Yeah. 11, T is 11, yeah. Oh no! What do we say the n was? N0. This is 7.8. And the lambda? Oh, sorry, my bad. It's not 1.5. I was looking at, this is for the activity. Yeah, the activity will be 1.5. Yeah, okay. So, we go back here. So, Ibrahim here got 8.62 atoms. Now you realise a small problem with this formula is you can't really get 8.62 atoms. You can only have 8 atoms or 9 atoms. Yeah? Did you hear that, Louise?
No.
I'll say it again.
Sorry, because I can't get the answer.
Oh, you can't? Show me your calculator. Yes. Yes. This is what's wrong. You, that's a big problem. Oh, at the time, I said the time is 11 seconds. Now, see?
So what the time is the 11?
Oh, that was my question. I said here, whoops, what is n at t equals 11? Yeah. Okay. Now, we'll go to the next room in a minute, but before we go, I want to comment on this here about the point. So, you can see here, you can't have 57.8 atoms. It doesn't make sense. You can only have 57 or 58 atoms. And here, you can't have 8.62 atoms. You can only have 8 or 9 atoms. In fact, what's happening on the graph, when you graph your your M0 E minus lambda t, we graph it nice and smooth like this. But what's really happening is the graph really looks like this. It's not smooth. You know, for example, maybe here is 8 atoms, and then it decays to 7, and then to 6, and then to 5 and 4. You know what I mean? It's not actually a smooth graph. Yeah, it's like stairs. But that's a very small price to pay for having such a nice, neat formula. You know, so just remember, the answer is not exactly 8.62. You know, it's about 8, it's about 9. Like I said, it's a small price to pay for having such a nice, neat, smooth, simple formula. In fact, in the exam, I feel like they would like you to keep it as 8.62, unless they tell you to round it off. But I think if you said 9 atoms, because you can't, if you said in your answer 9 because you can't have 8.62, I probably will still give you the mark. But you see, usually atoms are so big, we need a number like, kiloatoms, or megaatoms, or even moles. And then when you're using moles, of course you can have 8.62. It's not a problem. Yep. Now, what room are we in next? D207. So what I will do is give you some graph paper, and we'll practice doing this one neatly on graph paper for the exam. Okay? And then we'll go on to the last radiation topic. So we'll do a little bit more of this in D207. Yep? Okay.